some algorithmic, algorithmic or discrete representations. So you will have to find natural representations where we try to do something, then use probabilistic analysis. And the game is, at least in this talk, to find interesting continuous results. So you want results mostly about the continuous. Okay, so I'll explain one of the main tools, and you will see that basically everything comes from this. So it's about graph exploration. So the basic idea is you're given a graph. So a graph is just a set of nodes, and you have edges between the nodes, so links, and you want to understand what is their structure, what is their geometry. So one very nice and simple idea is the following. You want to explore the graph, and from this exploration, devise some things about the structure. So what is an exploration for me? An exploration is just an algorithm that will step-by-step move in the graph to discover some of the local structure. So it's important that it will be local. And if you are thinking of a random graph, one things that are the things that are really important is to try to control what is observed. Because basically what you want is, like, as you explore the graph, you don't want to mess too much with the randomness. You want to explore as little as possible to be able to kind of generate the graph as you explore it. Basically, you want to think of it as a Markov process, and whatever you have not explored, if you can control the distribution of what you've not explored, you can basically generate it step by step, rather than just like taking a huge graph and then really exploring it. So one of the main examples, and we'll see where it leads, is a breadth-first search algorithm. So you can do it in a graph, you can do it in a tree. I'll just like show quickly what it does here. The idea is the following. You start from one node, and you want to maintain a set of discovered vertices that are yet to explore. Okay, so assume that the set of nodes to explore is A1, then A2, A3, and so on. At step I, it will be AI. So initially, you put vertex 1, so your nodes are labeled. Let's say they are labeled from 1 to n. You put 1 in your pile, and at each step, you will do the following. Yeah, you take the first node of the pile, you look at his neighbors. Whatever the neighbors are that you've not seen yet, you put them at the back of the pile. Okay, so this is this drawing here. And you keep going like this. So for example, if you go to the left, at some point, you have the blue box, which contains the pile of nodes, and maybe the red thing is basically the node that is the first in the pile. You take it and you add to the pile the new node that you've discovered, and you keep going like this. Okay, so you have an evolution of a pile. You remove one and you add the ones that you have not seen before. Okay, so doing this, you will explore all the graphs, and at some point maybe you don't see anything connected. If you have not seen anything connected, you take another node, any one, and you keep going like this. Okay.
Just a question, Nicolas, please. How you choose the first node A1? Is it the most left, the most right node, or?
So far, it's so far, like if you do it like this, what I want is like you start with A1, which is just 1, and you put them in order. So every time you put the first guy in the list, it's ordered. You put the guy on the left, you take the one from the left, and anyone you add it to the right. Okay, so you always pull something from the left and you always add to the right. So always there's a first guy, you always take the first guy. Okay? You could take some other policy. This one is some policy. Is that fine?
Yes, thank you.
Okay. Okay, so this very, very simple algorithm has been used by Aldous to find something that was like a long-standing open problem for some time, is to find the distribution of the sizes of the connected components of the classical random graph in the critical window. Okay, so let's pull back a bit. So the classical random graph, GNP, which has been introduced by Erdős and Renyi, you have n nodes, and between any two nodes, you put an edge independently of any other edge with probability p. This is GNP. Okay, so it's been well known for a long time that when p is about c over n, for c lower than 1, you have very small connected components. So the largest is of size log n. If p is c over n for c bigger than 1, then the largest connected component is linear in size, so it has size something times n. And if you remove it, all the others are very small. But it happens that you take something that is c over n for c equals 1, or something close, so like 1 over n plus lambda over n to the 4/3, so there's a little correction of lambda into the 4/3, then you see something completely different. You see sizes of connected components that are of order n to the 2/3. And what Erdős did is that he used the previous algorithm, so the breadth first search, to find the limit distribution for the sizes. Okay, so I'll tell you basically what he did, and you'll see that it's once you have the right ID, there are very few technical details to fill up. Okay, so what he did is he looked at the size of the pile. Okay, you have this AI, you look at the number of nodes in this pile. And what you want to do is you want to estimate the size of the pile. The first thing to notice before we actually do that is that what is the size of the pile? So the size of the pile is the number of nodes that you have yet to explore. So what happens when you finish the connected component? Every time you finish a connected component, you end up with an empty pile. Okay, you end up with an empty set and you're done. And conversely, when you have an empty set, you have just finished a connected component. So that means that if you just look at the size of the pile, you can recover the sizes of the connected components by just looking at all the times when it reaches 0. Okay. So what Erdős did is the following. He did in GNP, you can actually find exactly the evolution of the pile. So what I will do is rather than using exactly the size of the pile, because the size of the pile is a bit annoying because it is a reflected process, it has to be positive. So you want something that is nicer, that can go negative, but from which you can recover the size of the pile. And this is the xn lambda process that I introduced here. So you want to have the process xn lambda, which is 0 at time 0. And then it evolves in the following way. So the increments are -1, because you remove a guy, plus the number of new neighbors. Okay, so it's basically the same evolution as the pile, the size of the pile, except that you allow it to go negative. Okay, so once you have this process X, you can recover the size of the pile by reflection. Okay, the size of the pile is just 1 plus the value minus the minimum of the process between 0 and I. Okay, so you take the reflective process. So for now, we'll just like look at, okay, forget about the reflection and just let's try to figure out what is the evolution of this xn lambda process. So we've seen that it's like every time you take one node, this is the -1, and you add the neighbors. So you just have to figure out how many neighbors you add. What is the distribution? But if you've already done k steps, the number of new neighbors are what? This is exactly, there are k nodes that you've seen already. There are n minus k that are potential neighbors, and there are some in the pile. So the number of new neighbors is just n minus I minus the size of the pile. This is the ones that can be neighbors. And for any single one of them, it is an actual neighbor with probability p. Okay, so that means that we have exactly found the distribution for the increment. And this binomial is independent of the process up to time I. And it's easy to see that, like, if you just look at expected value and variance of the increment, you can find that like the expected value is say I over n plus lambda n to the minus 1/3, and the variance is 1, which means that basically, if you rescale properly, you will find the following result. So this is exactly what Aldous did. So Aldous proved that if you look at this process at time about n to the 2/3 times s, and you rescale it by n to the minus 1/3, why? Because of this estimate for the variance, you know that the limit will be Brownian up to basically the correction for the mean. Okay, so we proved that there is a limit for xn lambda over n to the 1/3 at time n to the 2/3 s to a process which is the mean, which is lambda s minus s squared over 2, which is the sum of the expected values rescaled, plus a Brownian motion. Okay, and well, remember, we don't really care about this process x. We care about the size of the connected components. And we know that at the discrete level, the size of the pile, so the size of the set, is the reflection of the process. So you want to do the same. You hope that in the limit, you can do the same thing, which means take the reflected process, and that from this reflected process, you can infer the sizes of the connected components. Okay, so this is what we'll do. So the limit process here, so lambda s minus s squared over 2 plus the Brownian ws, you call it x lambda. You take the infimum process of this between 0 and s, you call it x underscore lambda s. And you look at the points z lambda where the process touches its infimum, okay? And you know that these points is the equivalent in the continuous of the points in a discrete where the pile becomes 0, okay? So it should be the case that if you look at the sizes of the length of the plateau of this process, that is the length of the intervals between the points of z lambda, you should find the sizes of the connected components. And this is precisely what Aldous proved. So you call gamma lambda the vector of sizes of the length of the intervals of r plus minus z lambda. Okay, you can prove that there is the first one, there is a second one, and so on. So it can be ordered in decreasing order and indexed with the natural numbers, and you find the following. So if you look at the connected components in GNP, so the random graphs, at probability p lambda, which is 1 over n plus lambda n to the minus 4/3, you order this connected component by decreasing size, so C1, C2, and so on. You rescale the sizes by n to the 2/3. Then this converges to the length of the intervals that we've defined before, okay? So basically, what this says is like, what should happen, happens, okay? Because in discrete, the length of these intervals are precisely the sizes of the connected components. And it actually happens that this is true in the limit, okay? So there's a few details to be filled up here, but there's nothing too serious. So what is interesting with this is that you can actually couple all the GNPs for all the P in the following way. So what I said before is like to construct GNP, you put an edge between two nodes with probability P independently for every edge, okay? So you can construct this by assigning a uniform random variable to every edge and saying that there's an edge if the uniform is lower than P, okay? So if you do this, then as you change P, you really see an increasing collection of graphs, okay? That is increasing for the inclusion. So you see that there's a coalescent process when you do this. As P increases, you see that the connected components merge together. So because you have this coalescence in the discrete process, you must have the same in the limit in some way. Okay, so that means that the laws of the vector, gamma 1 lambda, gamma 2 lambda, etc., are consistent with the coalescence. And this is a coalescent in what sense? This is a coalescent in the sense that if you change P, which here corresponds to changing lambda, the small correction in the probability. When you change lambda, when you increase lambda, the vectors should be such that they merge together, like the pieces of the vector merge together to make a bigger components, okay? Something else that you can notice is like at the discrete level, how is that coalescence? So in the discrete, wait a minute, I'm going too far. In the discrete process, if I tell you that for a given P, you have a fixed graph that I tell you what the graph is, the next edge to appear between any two components is uniform between any two components, which means that like two components will merge with probability proportional to the number of potential edges that are between them. But the number of potential edges between them is exactly the product of their sizes. So that means that you have a coalescence that is multiplicative in this sense, okay? The rate to merge two connected components is proportional to the product of the sizes. And so Aldous used this to prove that there exists a limit coalescent process that has these dynamics. Okay, so the problem is that this is true for the laws. So we proved that because the laws are consistent, there must exist a process that corresponds to these dynamics, but it is not clear what the representation should be. The reason is the representation that he has with the breadth first search is given for a fixed P, okay? So for a fixed P or a fixed lambda, you obtain a given process. But if I change now, if I take this process and I change a little bit lambda, basically you have connected components that will merge together, but it will become a huge mess in the process. The reason is the order in which you see the nodes in the exploration is not consistent with the coalescent. So there's no reason why it should be nice. It will be a huge mess. And because of this, there's no clear representation of the process. And the first thing that we should try to understand is can we couple all the processes in such a way to have a nice representation for the coalescence, okay? So the idea is now, so we know that the laws of the vectors are consistent with a coalescent, but what we want to do is we want to find the coalescent. We want to see it, okay? And so for this, what we'll do is we'll try to define some order at the discrete level that is consistent with the coalescent. And you'll see that basically what I will do is like I will construct this order, and then basically we'll say like you see it has to work. And so what is this order? So the order is the order in which you see the nodes in Prim's algorithm. So what is Prim's algorithm? So Prim's algorithm is also an exploration, but it will not pick the nodes in any order. It will do the thing as follows. So my order will be V1, V2, Vn. So I will say that V1 equals 1, and then I will define Vi inductively step by step. So basically, at any step, what I will have is I will have a connected components that I see on, say, I-1 nodes at step I, and I will find the cheapest edge that connects what I've seen already to the external, okay? And so for this, I will need a weight. And so the weight will be uniform on the edges. So I will take the complete graph, I take all the edges, and on each edge, I put distinct edge weights. They don't need to be uniform for now. They will be uniform later on, but it doesn't matter for now. What I want is that they are distinct for now. So what you do is like at step I, you look for the cheapest edge that connects the set of nodes V1 to Vi-1 to the outside of the world. And you say that the new node is called VI, and the extremity of the edge that is in V1, VI minus 1 is called UI. Okay, so at every step, you add an edge. And doing this, you build a tree, because each time you cannot create a cycle, because you always shoot to someone that you've not seen before. Okay, so it turns out that if you do this algorithm, it creates a tree. And this tree happens to minimize the sum of the edge weights, which is like, you can understand why it should be the case, because each time you add the cheapest edge. And so it turns out that the tree that you built is the minimum weight spanning tree. So this is the tree that minimizes the sum of the edge weights on the edge. Okay, so what is interesting for us is this order. So V1, V2, Vn, you built, so you look at all the weights, and with all the weights, you define some order. Okay, and this order will be random if the edges are random. But what's nice is that this order is consistent with percolation in the following sense. That is, if I look at the graph GP, which consists of all the edges that have weight at most P, okay, then all the connected components in this order are intervals, okay? That means that if I take the increasing, if I increase P, I will always connect intervals that are next to each other. And because of this, there's a way to actually maybe see the coalescence if you explore it in this order. Okay, so first we'll see why it should be true. So essentially, you do it by induction. So when P equals 0, the graph is empty, and every node is in a single connected component. So it's true that all the connected components are intervals. Okay, and then you see, like, assume that it's true until you have added, say, a number of edges, and you see what happens when I add one more edge. So when you add one more edge by increasing P, what happens? So this edge is some edge of the minimum spanning tree. It's somewhere. Okay, so it's some EI for a step I. So by construction, you know that EI is the lightest edge between VI minus 1 and the complement. So in particular, VI must be the first node of some connected component of the graph that stops exactly before I add the edge. So if the weight of the edge is WI, then if I only include the edges with weight at most WI, so I don't include WI, then I have connected components, and VI must be a first node. Okay, this is the leftmost node of a connected component. And now you want to see, well, okay, we know that VI is somewhere. Where is UI? And we would like to prove that UI is in the connected component just before VI. Okay, so assume it's not true. So if it's not true, then there must be some M, and you must have the picture here. So I hope you see my mouse. So you must have this picture here. And then the edge you add must be the red one that jumps over a hole. So if you have such a situation, then the connected components will not be intervals anymore, and you have a problem. But you cannot have this. Why? Because, like, if you have this, then that means that the edge that connected VM, that is the one that is added at time M, has weight bigger than WI. But then why would you have chosen WM instead of WI? That means that the algorithm doesn't work. Okay, so you would never have such a situation. So if this happens, you would actually connect. So WM will not be like this. So in other words, you must have that the extremity of the edge must be as in the picture above. You must have the first node of some connected component, and the extremity must be in the component just to the left. Okay, so something else that will be interesting for us later is that now assume, so this is true regardless of the weights. Okay, they just have to be distinct for simplicity. But now, if they are uniform, if the weights are uniform, what happens? If the weights are uniform, we can say more. Because if the weights are uniform, and I tell you these two connected components merge together, and I condition on the graph at time wi, then the node ui must be uniform on the left. And why is it? Because like I give you the graph just before I had the edge. Well, any edge between any of the nodes of the connected component is equally likely to be connected to the I as the lightest one. Therefore, the one that is chosen is uniform. Okay? So that means that you have actually a way to sample the minimum spanning tree in the following sense. So if I tell you that I give you the prim order, V1, V2, Vn, and I tell you the coalescent, I tell you exactly which intervals merge at which time. The problem is that that is actually difficult to figure out, but well, assume what we know this. If you know this, then each time two connected components merge, you can exactly construct something with the right distribution by connecting the leftmost vertex on the right to a uniform vertex on the left. If you do this, at the end, you obtain a tree that is distributed exactly like the minimum spanning tree. Okay? So the only caveat is that, well, it's not so clear how to figure out what the coalescence events are, because it's actually difficult. Okay? Okay, so now we can actually use this to figure out what the coalescence are. And the reason is we will just do exactly what Aldous did, except that instead of using the order that is the breadth first order that Aldous used, we will use the prim order. Okay? So you will define an equivalent process x and lambda, and the excess x lambda will be essentially, so what I call the y and lambda I is the equivalent of the size of my pile. Yeah, someone asked a question? No, okay. So it doesn't really matter what the definitions are, like the encoding, you can forget about it. What matters is that you take the nodes in the order that I gave you, V1, V2, Vn, which remember, this order depends on all the weights. So this is a random order, and it could really create a huge mess. But the following is true. If you fix lambda, and you look at the number of nodes that are connected to the right of Vi each time, so this is exactly the equivalent of the Aldous pile, but in a different order, in this random order, then the law of the process x and lambda, which is defined in this way, it doesn't really matter how it is defined, is exactly the same as the one of Aldous. In other words, he has already done the hard work. So we know that if we rescale this process, it will converge to the Brownian motion with parabolic drift that we've discussed before. But what's more interesting now is that now we have consistence. We know that as we change lambda, the nodes stay at the same place because the order is fixed forever. Okay, the order is random, but it is fixed forever. And because of that, it actually turns out that as you change lambda, the only difference between xn lambda 1 and xn lambda 2 is that there is some averaging things that happens, is that the only thing that differs between the two is a linear drift. You add a linear drift. So there's always, so I will go to the next page and I'll come back after. So you can define xn lambda with a single Brownian motion. You add a drift, which is lambda s minus s squared over 2. And the lambda is really the lambda from the probability. And this process with the single Brownian motion will be the limit for the process that we have here for lambda, which means that if you take k values for lambda, it will jointly converge to a vector of k processes, which are essentially all the same, except that there's a linear drift that is additive between different ones. So you take different values for lambda. But now that is very nice because What happens if you change lambda? If you change lambda, well, you see that the process increases, okay? And you remember that the sizes of the connected components are exactly the length of the intervals between the points where the process touches the infimum. But as you add the linear drift, you have less and less points where it touches. Oh, I will try to do it again. So you have this thing. You start with something like this for a small lambda. You increase lambda, so some points disappear. You increase again lambda, so more points disappear. Okay, so it actually turns out that if you look at the collection Z lambda, which is the set of points for which the X lambda touches its infimum, then this is really decreasing in lambda. So as you increase lambda, some points disappear, which means that now you really see that there is a real coalescence in the on R plus in some sense. So what we've proved with Jean-François is that the process gamma lambda, you remember we had a gamma lambda that was coming from Aldous. Now we take the gamma lambda that comes from this process, where now everything is coupled together. So which means that now not only the laws are consistent, but the gamma lambdas are consistent. As you increase lambda, you really see pieces of the same vector that merge together. So we have proved that this is a strong Markov process, because it is not clear at all that this should be Markov. Why should it be Markov? And not only it is Markov, but it is homogeneous in time. And any two fragments of the vector, which means you take any two components, they merge at rate which is the product of their length in time. Okay, so this is exactly a clean representation of Aldous's process with a single Brownian motion and a parabolic drift, and you change the drift. You change the drift and you look at how the pieces merge together. Okay. Oh, I see that I'm very slow, so it's really unclear how far I will be able to go. So in the next 5 minutes before it's 50 or it's 45. Okay, like you stop me when I should stop. Like I have until 45 or I have until 50.
Encore 25 minutes.
Encore 5 minutes?
25.
25. Ah, okay. Okay, so it's fine. Like for some reason I have a bad time here, but okay. So that's nice. We managed to couple the different values of lambda together to see a fragmentation or to see a coalescence in as you increase lambda. But now you see all that came from this very nice algorithm, this prim algorithm. And that means that what underlies all this is the minimum spanning tree. And it turns out that not only we can actually figure out what the coalescence of the components are, but we can actually figure out what the minimum spanning tree is. And you remember that I gave you an algorithm to sample the minimum spanning tree. Given the fact that I tell you which are the connected components that merge together, okay? If anytime any two components merge together, you want to connect the two intervals by adding an edge between the leftmost node on the right and the uniform node on the left. Okay, good. So we will use that to actually find more about the minimum spanning tree. So it actually turns out that the scaling limit for the minimum spanning tree is already known. So we've done it with Luigi Adario-Berry, Christina Goldschmidt, and Grégory Miermont. So a couple of years ago, we've proved that if you take a complete graph, so just as before, you put uniform edges on the weights, just as before, you construct the minimum spanning tree, and then you forget the weights, okay? You just want to look at the tree, you use the weights to construct the tree, and then you forget about the weights. So you want to see the graph or the tree as a combinatorial object. So this combinatorial object will be defined by the graph distance on Tn, and we will add the empirical measure on the nodes, but it's not very important. So what we've proved is that this metric space, which carries the measure, converges in distribution to something. So it converges in distribution if you rescale the distances by n to the minus a third, and you just rescale the, well, you have a probability distribution, you just keep the probability distribution. So it converges to something. So, okay, so I'll tell you a bit first what this convergence means. So this is a pretty bad picture of a simulation, but it's just like pixelized a bit, but it doesn't matter. So it looks like this. You take a big one, you draw it, it will look like this. And what does the convergence mean? The convergence means basically the following. If you look at all the first order parameter in distances, they happen at the scale n to the 1/3, and they converge in the sense that if you look at the matrix of pairwise distances between any fixed number of points, say random, the distribution of this matrix will converge. The diameter will converge, and so on. And maybe more intuitively, there exists a way to couple the randomness of all the values for all the n and the limit in such a way that for n large enough, you can basically take two isometries of the limit and the tree for large n. You embed isometrically the two in a space, and it is possible to do that in such a way that the two copies are essentially isometric. Okay, so they are close in for the Hausdorff distance in this new space. Okay, so basically it means that they are close enough that you can basically put them together and you cannot see the difference anymore. Okay, so yes, okay, so it's nice because it proves the convergence. You know some things about the limits. So it's a tree, so it's a real tree, it's continuous. You can say things about the degrees, you can say things about the fractal dimension, but basically it stops there. So of course it should be a tree because you start from a tree. So if you have a tree and you take a limit and in the end it's not a tree anymore, then it's probably not an interesting convergence. So the second thing is that the proof is a Cauchy sequence argument in distribution, so for the laws, which means that there's no simple or explicit construction for the limit. The only thing we know is that it is not trivial. So we didn't divide by too much. So it's not a point. It's still random. And so there are many things that are still open, like what is the distribution of the distance between 2 points, 2 random points? What is the Hausdorff dimension? And so on. And so what I'll try to explain in the rest of the talk is that Prim's algorithm actually allows to construct explicitly a version of this scaling limit. Okay, and I will not construct it. I will basically tell you what happens in discrete and say, well, in the limit, it has to work in the same way. Okay, so the idea is exactly what we have said before. You want to first focus on the structure of the merges. And if we know the structure of the merges, then given that, you can focus next on what are the edges. And it turns out that, so the structure of the merges is a mess. Why? Because, so I've told before that like the edges are added uniformly between interconnected components. Okay, good. So before I put any order, the merge are simple. I just take a uniform edge and I see which connected component it connects. Well, okay, fine. But once I put an order which is random and depends on all the weights, this is gonna be a mess. Okay, so it's a mess in discrete. But it turns out that it is not a mess at all in the limit, because we've seen that we can describe this only with a single Brownian motion that you shift. You shift the slope at 0, and it works. Okay, so there's a hope for step 1. Then step 2 is what are the location of the endpoints? But, well, the location of the endpoints, we know what it is, because we've seen that in discrete, anytime 2 connected components merge, you connect the leftmost points on the right to a uniform point on the left. So what if we were just doing that in a continuous version? Okay, so essentially the idea is this: you want to do that. The only small problem is that it's easy to have this idea of dynamics, but the problem is that you ought to start from somewhere. So in discrete, it's easy because every edge counts for something. In continuous, and an edge doesn't exist. In continuous, you need to identify 2 points, but you can keep identifying points and still have nothing in the end. Okay, so this is the difficulty. So I'll basically tell you how you want to do this. And this, before I do this, like essentially the theorem is like, yes, we can do it. So there exists a metric space M that is the scaling limit of the minimum spanning tree, and it's a version of the one that we've constructed with Luigi, Cristina, and Gregory. And you can further do some additional computation. So you can verify directly that it's compact. You can compute the Hausdorff dimension. I will not go in these considerations, but it's actually interesting to have it. Now, the question is, how do you do? And the basic motto is essentially, you find a very nice process that works exactly at the discrete level. And if you find the one that actually represents as nicely as possible the situation, usually life is beautiful and you can actually lift everything up to the scaling limit. And this is what happens. So basically, I'll just tell you about what happens in discrete, and you'll see that you can basically do the same in continuous. So what happened in discrete? So the first things to observe is that you just need, if you want to find the connected component, or sorry, forget what I said. If you want to describe the minimum spanning tree, you just want to find the path between any 2 nodes. So if you can identify the path between any 2 nodes, then you're done. Okay, in discrete, this is clearly true. And it turns out that the tree is well approximated by the minimum spanning tree of the largest connected component for large lambda. So that it's not clear that it should be true, but it is true. And we will just admit it. So essentially, when you take a huge lambda, you will have a huge parabola for the Brownian motion. It will contain a huge part of a huge interval, and that will basically tell you something that is close to the metric of the actual minimum spanning tree. Although in there are only big O of n to the 2/3 nodes. Why? Because like we know that the scaling process is the process is rescaled for time in n to the 2/3. So whatever lambda you take, you will only have n to the 2/3 nodes, but still the metric is correct or almost correct. Okay, so we admit this. So now for fixed n, we can choose 2 points, xn and yn, which is x n to the 2/3 and y n to the 2/3. Okay, you just take 2 points that are in the right region. Now, for these 2 points, you want to find the path between these 2 points. So how can you do this? You will first increase lambda until they are in the same connected component, because before they are not connected. So once they are in the same connected component, now you start decreasing lambda until they disconnect. And at the time when they disconnect, basically you know exactly the distribution of the edge that connects the two, because at the time when they disconnect, you know that you took an edge, this is the red one, in the minimum spanning tree, and it disconnects the thing in 2 pieces. I don't tell you what the pieces are, the white intervals, but yn is somewhere, xn is somewhere. There's a white connected component to the left, there's a white connected component to the right, and there's an edge, red, which connects the two. And if you want to go from xn to yn, you need to use that edge. There's no other way around. So you know that that edge must be in the path. So that means that the point vi must be in the path, and the point ui, which is uniform on the left, is in the path. Okay, but that's good. So if you want to find the path between xn and yn, you just have to do this and recurse, because then once you have the first red edge, you need to find the path between xn and ui, and you need to find the path between yn and vi. And you keep going like that. And if you do this in discrete, in the end, you will find exactly the set of points that are on the path. Okay? So on the right, I've put them in order. But what is this set of points? This set of points is just a collection of points that is on the line which is of length about n to the 2/3. But we know that the distance is of order n to the 1/3. So the number of points that you find is about n to the 1/3. So they are scattered everywhere, but you know that these points are there. Okay, good. So you can do this for any 2 points. It turns out that you just want to do the same. So you know that in the continuous, you have a way to recover the white intervals every time there's a disconnection. And so there's a way to basically do something that is very analogous to this. And this is what you want to do. So in the continuous version, this is actually much nicer because the process xn lambda is a real mess. But the process x lambda in the limit is much nicer. This is just a Brownian motion plus a parabolic drift. And the parabolic drift changes as lambda changes. This is it. So that means that you will just take a single Brownian motion and you will make it like change as I showed before. And with this, you can construct the path in the following way. So you take any 2 points, x and y, in the continuous. You take lambda large enough so that they're in the same excursion of the process. Then once you've done this, you basically decrease lambda until you see 2 excursions that disconnect. And exactly at that time, there are 2 points. There's the point that will disconnect the 2, the kappa xy, and there's a uniform point to the left. You just sample it. And then you will recurse. And you know that to go from x to y, you will have to go from y to kappa, and then from x to eta, because there's an edge somewhere that connects eta and kappa. And you want to do like something like this. So if you do this, you'll basically proceed like this. So here, maybe it's clearer. You take this excursion with x and y, you take it large enough so that they are in the same connected component. You decrease lambda by decreasing the drift until they disconnect. At the time when they disconnect, it splits the thing into 2 pieces, and then you recurse on each side. Okay? So when you do this, you will construct a set of points. So my set of points is the set of points that disconnect and the uniform points. And you take the closure of this set. This will give you a Cantor set. And it turns out that you can think of this Cantor set as the set of points that are used to go from x to y. Okay, so there's no really point in describing the thing precisely. You take this this set, you can define it nicely, prove that it is not empty in the n, and blah blah blah. And so that basically what it tells you, it gives you for any 2 point xy a way to construct the path between x and y. So it's only a set of points, but there's a way to recover distance from this set of points by just some Hausdorff measure. And so what does it give you? It gives you an explicit construction of the scaling limit. So you see, it's explicit, it's a bit of a mess, but it's explicit in the sense that it's a measurable in just given some random points and the Brownian motion. It's still complicated, but it allows for some computation. So as I said before, if you do this, you can directly verify that the space is compact. You can directly compute some fractal dimensions. And there are still many things that we cannot do, but we're already happy with this description. And I'll stop here. Thank you very much.
Thank you for you, Nicolas. Thank you for this nice talk. Are there some questions, please? Are there some questions, please?
Oui, bonjour Nicolas, c'est Cyril Bandorier au bout du fil. Question éventuellement. Oh, sorry, perhaps in English. Sorry. So I have a question perhaps on what you call reflected process, because you can consider it either as perhaps the absolute value of a bridge, then you have the reflection of a bridge, and it has a given distribution, or you could consider it as what you call what we call excursions, a dig path.
Okay, okay. What I call reflected is really, so you take the process, you take the infimum process, and you take the process minus its infimum. Because if you take the absolute value, this will not work. Okay.
Okay. Yes.
See that exactly. The evolution is the right one above the minimum. So you know that the increments are correct. And so to recover something that is still correct, you cannot take the absolute value, because if you take the
yes, the distribution
the absolute value,
same.
The law is not correct, because
exactly.
you will swap some things that should be pluses into minuses. You know that the thing that is important is you can only have a -1 and all the rest is positive. If you take the absolute value, this will not be true anymore.
For example, but for your process, do you know the distribution of the numbers of returns to 0?
In discrete?
Yeah. Or average?
Exactly the distribution? No. I don't, but
because it could be
I would say that probably you
exactly
can do it. Exactly, I would be surprised, but.
That's Andrea.
Yes.
Well, I believe that such a question cannot be solved by the continuous limit, because the number is dominated by the small components, which are intrinsically discrete.
Oh yeah, so in the continuous, that's right. You're right.
So I mean, evaluating the distribution for the number of components would mean not using the 99% of the techniques that you use and restart it all over, essentially. Because the probabilistic question you can answer are those which are associated to the large components.
That's
those which are associated to the small ones.
That's true, but it's not completely true, because if you look at, so you take the discrete process, and so in discrete, the number of connected components that you've seen by some time is exactly the number of zeros, or the number of points where you touch the minimum. But it's actually more than this, because you see that every time you have a new process, you also go down by 1. So this is a new minimum, and the minimum can only increase by 1, which means that the number of times that you've touched the number of components in the reflected process is exactly the value of the process when you don't reflect. You see? Does it make sense?
That's your claim, is that you have
this is just the value of the infimum process at some point, period.
Yeah, I agree.
So that has to converge.
The claim is that the distribution is essentially given by lambda minus sigma square, I don't remember, plus Gaussian random variable, which is what you knew already from Aldous, right?
Oh, okay, that's okay. That's correct. So I don't know what Cyril's question was, if he wanted exactly the thing in discrete, but exactly discrete I don't know. But if you rescale, if you look at the number of connected components and you divide this into the 1/3, then it will converge to the thing in the limit.
Yes, because there is possibly a paradox. The number of returns to 0 when you have when you consider Brownian motion, and when you compare with discrete Dick excursions, then you have kind of square root of n renormalization, which means a return to 0 in the discrete is really a 0. It's not up to the small o of square root of n. And if you look at the Brownian motion, it's small o of square root of n. So the discrete.
No, it works.
No, but they are not the same. One will be big O of 1, and the other one will be square root of n.
But there's a rescaling, of course. So if you take a dig path, it's the same as for a dig path. if you take forests, you take a forest rather than a random graph, you take a forest, and then if you take a forest, it will be exactly Brownian motion. There will not be a drift, parabolic drift. If you take a forest and you look in the limit Brownian motion, of course, there are infinitely many zeros.
Yes.
Okay. But if you look at there is some Hausdorff measure that you can put on this set of zero that gives you exactly the right thing. The second thing is if you look at the minimum of the process,
yes,
this gives you the limit, the infimum of the process in the limit, which is already rescaled. It will give you the leading constant in front of the square root of n. Of course, you don't whatever is little of square root of n, you don't see, but you see the leading constant and it is correct.
Okay, but what I was meaning is when you have a return to zero in a Dick excursion, in the discrete case, it's really altitude zero. And
yes,
when you go to the Brownian model, you cannot make the difference between altitude zero and altitude one.
That's correct. That's correct, but you cannot. But it works. The reason why it works is that there's some averaging. Every time you are close to zero, you will touch zero. And because of the averaging, it works. It works because of some averaging, but it works.
Okay.
Mm-hmm. Okay, it will be long, but we can discuss it later if you want. It's surprising. That's correct, but it just works because of some averaging. It's like it's something that is well known. It's related to local times, things that have been studied by Yor and a number of others.
May I make a small modification to the sentences said previously?
I don't hear you very well. But
let me see if I have. Okay, I put my volume up.
That's fine. That's fine. Perfect.
So I said previously that the average number of components at given lambda is more or less given by something like lambda plus constant plus Brownian motion. And that's already given essentially by Aldous because the construction is the same. But let me now correct this sentence. Now you can answer to the question, what's the joint probability distribution that at k different values of lambda, lambda 1, lambda up to lambda k, there are n1 up to nk components.
Yes.
Because in your process, the coupling will allow to explain this joint probability distribution that Aldous didn't have, right?
That's true, but the question is also different because like you see the number of connected components that you see by some time depends on the exploration. And so if you take a different exploration, of course you find something different. So if you were doing the same in Aldous, you would basically, you would have very little correlation between the different values.
Okay, I agree. There is a coupling, but the coupling is a natural coupling. Say that you have only two values of lambda, lambda 1 and lambda 2.
Yeah,
then you have edges of three colors, edges which are always there before lambda 1, edges which are never there above lambda 2, and edges that occur between lambda 1 and lambda 2.
Mm-hmm.
So this is just the natural coupling, the coupling by inclusion.
Yes.
So it's not really prime specific. It's just given by the total order that you have. It's canonical. It's more canonical than doing prime.
I don't understand this because you still have the first. So everything depends on which point you put first, and the order will be really different. So the big connected components will stay mostly at the same place because they are there anyways. But the order in which you pick them might be different. But
the number is the same.
Why?
Because the number is canonically defined. It's just the number of components in this filtration model.
But it depends. But that is the number of connected components that you see before some time. But it is, in which way is it canonical?
It is canonical in the sense that it is. You said at the beginning that you have a total ordering on the edges of the graph.
Yeah. Oh, yes, but I don't start from the cheapest edge.
Exactly. So you
I
have a
start
total
from
ordering on the edges.
connected to node number 1. So if I start from node number 17 or from node number 23, this will be a different order. But it will change. I agree with you that basically just the beginning will be different, and then like it's mostly canonical, because once you change connected component, it's not clear. Like, maybe you see something that I don't see, but
well, I bet that if you think about that, you either agree with me or understand why I'm wrong. But my claim is that this is a rather canonical process. It's just the filtration by inclusion. And you, by using prim, which is less canonical in a sense, it's one way of exploring, you will have the joint probability distribution, k-point joint probability distribution with k only of order 1, for the number of components that comes out from this having a single Brownian motion and changing the drift alone. So this is my claim, which is either right or wrong. If it is right, it will be easily seen by you. If it is wrong, equally well, it will be easily seen by you that it is wrong.
Yeah, but I think it might change a lot when you, so these things should change, or at least could change a lot when you change the point that is the starting point of the exploration. The reason is that, so if I start from another point, you will see a different Brownian motion. You will not see the same. That makes sense?
But the distribution is only depending on the final point of the Brownian motion. And the other Brownian motion that you have will be just a reshuffling of the steps, but the total sum will be the same.
Okay.
I mean, I think
okay,
I'm getting too long here, but
no. Okay. I think you're correct that there should be some averaging. That basically, because you pick the largest guys first, they should at some point the sum should indeed basically be the sum of the large ones plus the tiny ones, which are basically count for a constant multiplication, and it should work. But you probably have something to prove. But that's correct. I think you're right. Actually, I think you're right.
Will you be in Bordeaux for GSB?
Probably not. Probably.
Okay, sorry. Now I really quit my microphone. Sorry for taking so long.
I have two small questions. The first question is, you have proven that you have convergence in some sense to a metric space with metric delta. Which properties have this metric, this limit metric delta? And the second question, you choose weights WE as uniform on 0,1. Why you choose 0,1, not other distribution?
Okay, so the second question is, I'll do this one first. So if you take something that is not uniform, it doesn't change anything. The reason is because like you see that the exact distribution does not matter. The exact value does not matter. The only thing that matters is the order in which the edges are picked.
Okay.
And because of this, if you take any like absolutely continuous distribution, it will do the same thing. If you have equalities, then it's a mess, and I have no idea. Like, you need distinct points. If you have something where you have an atom, then I don't know what you have. But and then I didn't really get the first question about the metric.
The properties of the limit metric delta of the limit space.
Yes. What probabilities?
The metric. Sometimes you have proven that the space converges in some sense to a metric space with metric delta, I think.
Yes. So there.
Yes, yes, there.
Yes.
The last line. The last line.
So what is the delta? Okay, so I can tell you what the delta is. So if you go, c'est dans l'autre sens. I want this. Okay. So you take your Brownian motion with parabolic drift. You take any 2 points, and then you construct the set of points which are the zeros where you have the disconnection and the random points. So you basically add this, you start with the 2 red points, then you add the 2 pink, and you keep decreasing until you add something like a contour on the line. Okay, so this is only the set of points. And then you define some Hausdorff measure for a gauge function, which is exactly the one in blue, the psi of r, which is square root r log of absolute value of log r. You can define a Hausdorff measure for this. And if you take the Hausdorff measure for this gauge function on the set, which is the one of that we described, the red one, then you find something that is equal to the distance up to a multiplicative constant. So basically, and this gauge function is exactly the same that you use for the zeros of Brownian motion. So if you use, you take Brownian motion, you know that it has a local time at 0. And you can recover this local time at 0 by basically looking the set of points where it touches 0, exactly the set of points. So it is a perfect set, and you can measure it with a Hausdorff measure, which is exactly the same as that one. So that means basically that the nature between the set of points that the geodesics between the different points is in nature somewhat, it's very similar to the set of zeros of a Brownian motion. Locally, because of course the distribution is different, but it has the same nature.
Okay. Okay, thank you. Are there other questions, please? So, if there are no questions, we thank again Professor Nicolas Broutin for this nice talk.
Thank you very much.
Thank you. Thank you.
Thank you, Nicolas.
See you. Merci.
Yeah. Bye-bye.